So moving into electrical generation. Let's go here. As I've alluded to previously, AC is our primary electrical source, and we're going to ultimately use AC to create DC. But we have to generate AC in the first place, and so AC generation also has different kind of priorities for where we're going to try to generate it. And it's based on, when we're looking at priorities on an aircraft, it's based on that aircraft being in a flight configuration, because that's what these things are designed to do. And so your primary source is going to be your engine-driven generators. Anytime the airplane's in flight, unless one of these engine-driven generators isn't working, it's going to be running off of the engine-driven generators. The auxiliary sources, the APU, auxiliary power unit, has a generator, APU generator. And in some aircraft, they have a hydraulic-driven generator. Use a hydraulic system to spin a hydraulic motor, and that hydraulic motor powers a generator. Okay? Those typically are more of an auxiliary type source, okay? Which means if the engine, the primary source, the engine generators aren't available, then the plane will look for the auxiliary source. On something like, on an older transport aircraft, the flight engineer would have to switch these manually. On anything modern, this whole switching process is done automatically. That's why you'll see on a lot of these control panels, they don't have an on and off position, they have an auto and manual position. And normally those switches or controls are left in auto 99.9% of the time. The manual is only if for some reason the automatic, something fails and the automatic switching fails. So you gotta have like a double failure there. So, you know, say you power up an aircraft on the APU generator to get it started. Once you start the engines, the contactors and the relays will actually switch over the bus power sources to the engine generators without you having to do anything. You won't have to shut off the APU generator. Typically it'll automatically unload that one, disconnect it. All you usually have to do is shut the APU down at that point. The last one is your emergency, okay? These are kind of your main ones. Emergency can be an air-driven generator. We'll look at that. But you can use airflow to spin a generator using a turbine or a little propeller type thing. Or a battery with an inverter. So DC powering an inverter, inverter turns DC to AC. But you're going to be very limited in the amount of power you have in both of these cases. Okay, we'll look at how that works. And then finally, we have ground power. Sometimes it's referred to as an auxiliary source. Sometimes it's kept separate because in flight, you're never going to have ground power available. And it's the same thing. It kind of falls priority-wise. It's kind of at the bottom of the auxiliary sources. So if you have a plane on ground power, when you start the APU generator is going to take over. And then once you start the engines, the engine generators will take over. Okay. So here's what those engine generators look like. And this first type is and what's most common, besides the 787, and a couple newer corporate aircraft, is an integrated drive generator. And it's made up of two parts. That what you see here is actually two components that they typically come from the overhaul or manufacturer facility assembled together. If you're just working on the aircraft, you're never going to necessarily split one of these. They're going to be split in the back shop, and you're going to change them out as a unit. But you have your two parts are a constant speed drive. That's kind of the left half here. There we go. Here's our constant speed drive on the kind of left part. And then the actual generator itself is the right part here. And this little spline shaft on the very left is what keys into a female spline coupling on the gearbox, the accessory gearbox of the engine, in order to turn the generator. There's kind of another view of it. So we turn that spline shaft. You can kind of see some of the various areas and some of the different parts. These are, for the most part, oil-filled. And so they often have their own little oil system with a sight glass. They've got fill and fill and drain ports. They have oil in and out ports, and those are because they're going to have some kind of an oil cooler. You have to cool the oil because they're running constantly. Filter the oil in the filter, and the actual generator itself, you get variable speed in. You can see from the accessory gearbox, in this case on this aircraft, 4,600 RPM to 8130, right? Whether you're somewhere between idle and full power. But with a generator, you've all learned about generators in electrical, the RPM determines what? The frequency of the output of the generator. And so the constant speed drive takes this variable input and spins the generator at a constant frequency to provide that 400 hertz that our airplane is looking for. Okay? Again, in a plane that uses 400 hertz, which is most. There's a few out there that use a wild frequency. We'll talk about that in a little bit. So variable input speed, we get a constant output speed, and it does this using something called a hydromechanical transmission or a hydrostatic transmission. How many have heard the term hydrostatic transmission before? Few hands. Where have you heard the term hydrostatic transmission before? In a lawnmower. These work on the same concept as a lawnmower transmission. Typically zero turn, the ones with the two little handles, you push pull. I've got one, they're fun to ride around. My wife hates it. But you're going to have some kind of a axial gear differential, governor assembly, and then a hydrostatic transmission is essentially a hydraulic pump driven on one side, and it uses the hydraulic fluid from that pump to drive a hydraulic motor. And in this case, it's a single direction hydrostatic transmission. Whereas like a lawnmower, one can go forward, reverse, neutral. These basically have forward, but a range of forward speeds. Okay? And then you use oil and flyweights to control the output speed. So I do have a video that shows, now this is not a constant speed drive hydrostatic transmission, but rather it's more of a industrial or lawnmower. These are used in industrial settings as well. So this is an industrial one. It's actually a double. The one on the airplane is a single. I just can't find a good video of a single one that would be normally installed in an airplane. Apparently it's not a big market that anyone's made a video of. So hydrostatic transmissions, lawnmowers, industrial settings, constant speed drives, and integrated drive generators on transport aircraft. The other thing that these include is a system for automatic and manual disconnect, and that's shown here. So on this input shaft, just to the left of it, there's going to be this looking device. So here's the input shaft, and there's a spot where the input shaft and the shaft that actually drives the hydraulic pump in that hydrostatic drive, they can be physically disconnected right here. And the way that works is this is threaded. Normally this little plug is held in the down position. It doesn't touch this, but when it's released, it pops up. These teeth engage these threads. It's designed, the directional rotation is going to cause the shaft that goes to the pump to drive to the left. And that will physically disconnect the input from the engine. The reason for that is if we have a failure in this, these things are big. You know, the 50 passenger airplanes I worked on, these things weighed about 70 pounds, so they're sizable. So you can imagine the amount of stuff in them. If it were to fail, they can actually drag the engine down. And so this physical disconnect allows us to do that. Also, if it's overheating or if it's getting an overcurrent, we don't want it to catch fire. And so we stop it from physically rotating. So these, once they're activated, either they can be automatically activated by the generator control unit, which is a little computer that controls this, or by a button in the flight deck. Once it activates and this pops up, it stays in that up position until it's physically reset by pulling a ring. So it can't be reset in flight. It has to be done by maintenance on the ground. And that's what they show, this little reconnection ring on the bottom here. That's what that is. Okay? That's to reconnect, physically reconnect that. And the other thing that happens is if one of these does disconnect, you have to track the amount of time it's disconnected because they're only allowed to run for a certain period. You can only run this on a running engine for a certain period of time disconnected. We would operate these. A normal test is to press the manual disconnect button, make sure it disconnects. Then you go out, open your cowl, reset it. Then you start the engines back up. You have to stop the engine first. Don't try to reset them while it's running. You'll shred these teeth right here. You stop your engine, you go out, you reset it, then you run the engine again, make sure it's all reconnected. But you do test these every once in a while. Now we would pretty much hit the button, and if it worked, we'd shut the engine down. So usually the time is somewhere like 8 hours, 10 hours, 15 hours. So we weren't anywhere near that. It's more if it had to be disconnected in flight, or if it has to be disconnected in a flight out somewhere, and they're going to leave it disconnected for the flight back. You got to kind of track how long that's been. In addition to that, since that's a hydraulic transmission using oil, and it's typically engine oil, these are the ones, every one I've worked on was filled with the same oil that you used for the engine. It's a separate oil system, but they run on they use the same engine oil. That way you don't have to have a different oil for your drive generator than you do for your engine. And we had one type of oil, we ran it in the integrated drive generator for the generator, we ran it in the starter, we ran it in basically any accessory that required oil, it used turbine engine oil. That is also the hydraulic fluid that's connecting that pump to the hydraulic motor inside of there. And so that's going to get warm. So these often, almost every one of them has an external heat exchanger. They can be either an air oil cooler, that's what's shown here. So here's the actual IDG at the bottom, and then an air oil cooler here, and what you get is fan bypass air that travels through it. They can sometimes be a fuel oil cooler as well, where it'll pass the cold fuel in it on its way to the engine. I don't have a picture of one of those. Again, majority are more of an air oil cooler system. So there's some hoses, lines that come off these output and input ports. They run up to an oil cooler. Cold air passes over it, cools the oil, and then it flows back down into that. But again, it is a totally separate oil system from the engine itself. They never mix in normal operation. Inside, you have your three-phase generator. It's controlled by something called a generator control unit, or GCU. It's a little computer, okay, or a logic circuit. Not even a computer, but a logic circuit that operates these. And they have to be brushless, self-sustaining, and self-starting. And so the way that works is you have several layers of electrical coils, okay? So you have, this is the generator control unit here that has to get power. So there's a little fixed generator at the front with a fixed magnet. That provides, in this case, 30 or 38 volts to the GCU to run it. So you don't need the aircraft electrical system to run the generator control unit. You have this little permanent generator. So here's the engine driving that constant speed drive. And on this aircraft, engine speed is 8840 to 1750, and our constant output is 12,000 RPM with a governor. Okay, and this is the spinning magnet here, the PMG, permanent magnet generator rotor, is powering the permanent magnet generator stator coils to power the little computer, basically, that runs the generator. And then that generator is going to put out a current through the DC, the exciter stator DC right here. That is an electromagnet, okay? And when that comes on, that provides the magnetic field for this exciter rotor, okay? And then a rectifier that ultimately put out power for the aircraft. So it uses a permanent magnet generator to generate a small current to operate a bigger electromagnet to provide the field to generate power coming off of the main coils. And because of that, what happens is if your engine's running and this generator and this generator control unit are operational, you will get power out of your generator. It doesn't rely on anything else on the aircraft to be able to provide power. There's some control, you can turn it on and off manually, but ultimately, if there's some kind of a failure, if there's a failure of any kind of signal being sent to this to turn it on or off, it's going to fail into the on position so that you will have AC power available. So here's those controls. So, control and indication, you get a fault. There can be a fault indication if something's wrong and it gets shut off by that generator control unit. It's got a light that'll light up for a disconnect, and if you push this switch button, it will cause it to disconnect. That's that physical disconnect, where it pops the solenoid and disconnects the shaft. So generator power off, and then you can turn the generator on and off with the switch below. So there's your actual control. So you can tell it to be off, you can tell it to be on, you can reset. It's got an off and a reset. When you turn it off, it also resets the generator control unit in case there's some kind of a hiccup going on there. If you want to see this in detail, there's a good video about the A320 system. We're not going to watch it in class. I think it's about, I'm trying to remember if it's like 20 or 40 minutes of information on the A320 generator unit system. So if you want to watch that, it's there. It'll be, it's good information. It's basically what you would get when you're talking about this in a FAM class versus here where I have to do it in 5 minutes. Some aircraft, and when I say some aircraft, the main ones we can think of are the 787 and now the Bombardier Global in the business jet category, use a variable or wild frequency AC generation system. So it's similar to the integrated drive generator, but it gets rid of the constant speed drive. So it's basically just a generator. You still have the physical disconnect in there. So it's still got a little kind of gearbox thingy on it, so you can physically disconnect it. But rather than trying to put out exactly 400 hertz, this is just going to ride along with the engine. And for a lot of your loads, a lot of the items that use electricity, current doesn't matter. Sorry, not current, frequency doesn't matter. Current does matter. Current always is going to matter. Frequency doesn't matter. And what I mean by that is the wild frequency is directly affected by the engine gearbox RPM, which is directly affected by the power setting of the engine, where you have the throttles, somewhere between idle and full power. But what we're powering here is the 787 goes to a what's called no-bleed architecture. Instead of using hot air from the engines to, in particular, perform wing ice protection, we used to blow hot air through the leading edge of the wings. It has big electrical heaters in the leading edge of the wings. So basically the wing leading edges of the 787 have big resistors running down them. And a resistor doesn't care what frequency you're putting through it. All it cares is how many amps you're putting through it, and the more amps you put through it, the hotter it's going to get. So the other thing you have is that drive, the constant speed drive, is big and heavy. And by eliminating it, we save weight. So you get rid of the constant speed drive, you eliminate typically somewhere around half the weight of an integrated drive generator. You still have the big copper coils and everything to do the generation, but you don't need the hydraulic pump, and you don't need the hydraulic motor, and you don't need the flyweights and the control and the filtering. Some of these generators don't even use oil to cool them. They don't need to be cooled. Some of them do, some of them don't. It just depends. But it's a lot lighter, it's a lot simpler, it's more robust, and a lot of your equipment doesn't require it. And the other thing that we have nowadays is because it used to be you had to have that mechanical or hydromechanical drive to change that frequency, to change that output. Now that can be done with solid state electronics. I've pointed it out that you have, I've got it plugged in, that's right. This little box right here that's powering my microphone is taking 120 volt AC and is turning into 5 volts DC. That's a transformer rectifier. You can also take 120 volts AC and turn it into, 120 volts. You can take 120 volts AC wild and turn it into 120 volts AC fixed using a solid state box that's a similar size to that. So now, if you do have items that run on this wild frequency and they need a specific frequency, you can build that right into the individual item with very small, lightweight electronics rather than needing to use this big, heavy mechanical, hydromechanical drive. And so it's lighter overall to do that rather than if you don't need constant frequency everywhere, why create constant frequency everywhere? So that's what we're going to. That's the future kind of these things. Also, they're going to higher voltages so that you can run, you can get more power with the same amperage, essentially. APUs, as our secondary source, they use another, most of them, if you're on a 120 volt, 400 hertz, three-phase aircraft, that's what the APU generator is going to be. Now, these are mounted the APU gearbox, so there is no constant speed drive. Why don't we need a constant speed drive on an APU, auxiliary power unit? It's always going the same RPM. When we get to APUs, we'll talk about it. You turn it on, you start it, it gets up to what's called 100%, basically full power, and that's where it runs all the time. You're never running anything off an APU when it's not at its rated speed. And so you build a generator where the rated input speed is going to output 400 hertz. And you don't need any kind of a constant speed drive. So this is what a constant speed drive, or this is what a generator looks like from an APU. It's also what a wild frequency generator looks like if it's mounted on an engine. Often these are rated to the same KVA as the main IDGs. On smaller aircraft, large aircrafts, they struggle with that a little bit. So frequency is controlled by the APU running at 100% at full speed the whole time. Another secondary source is our hydraulic generator. So three-phase, 120 volt, 400 hertz generator driven directly off of a hydraulic motor. Why would we do this? Any ideas? How do we get hydraulic pressure? How can we get hydraulic pressure? With a hydraulic pump. How can a hydraulic pump be powered? So electricity, so that doesn't make sense. Why would we generate power off of an electric device? How else can we get hydraulic power? How else can we run a hydraulic pump? You're probably not going to run a generator off a manual pump, but good. So that's another. Any other ideas? The engine. You can have a hydraulic pump directly driven off the engine. So even if the generator on a specific engine fails, you could have the ability to still generate electricity using that engine, but going through the hydraulic system. So that's where these kind of systems come in. They're not going to put out as much power as a generator driven directly by the engine, but they can be, say on the ground you only run one of 3 hydraulic systems, you can run your electrical off of that as well. Okay. They're both being run off the engine. So the typical architecture, this is getting into like overall, looking at it as an ecosystem. Everything we're looking at here, left engine or number 1 engine, powers the number 1 generator, powers the number 1 bus, the left-hand bus. We'll call it left and right just to make it in my left. Right-hand engine, number 2 engine, powers the number 2 generator, powers the number 2 bus. Okay. Now, often you have a hydraulic system referred to as left and right as well. And what you would have is we'll call it the right-hand hydraulic system. That maybe would be powered off the left engine, and the left hydraulic system is powered off the right engine, but then the electric pumps for those are driven off the electrical system from their same side engine. Not confusing at all? So what it is say you have a hydraulic system. Every hydraulic system on transport aircraft is going to have at least two sources of energy for pressure, 2 pumps. One is typically engine driven, one is electrically driven. So say I have a hydraulic system, my engine driven pump would be, say if it's the left engine, my electrically driven pump would get its power from bus 2, from the right engine. So then you could use that system to power, if that hydraulic system drove a generator for bus 1, I could use the bus 2 electricity to drive the electric pump, to pressurize the hydraulic system, to drive the hydraulic motor that drives the generator that can send power to the number 1 bus. So now we're powering both buses off the right-hand engine, one directly from the generator and one via the hydraulic system. Uh-oh, I got people think, here we go. We'll do left engine, and right engine. Okay, right engine, we'll call it generator, powers bus 2. This is electric hydraulic pump for hydraulic system 1. Okay. Normally, gen left powers pump to power, Normally, left engine hydraulic pump powers hydraulic 1. You see how that works? So now if this generator fails, we can take pressure from here to power oxygen and put power into bus 1, rather than getting electricity through gen 1 to bus 1. This isn't here anymore, so now we can go like that. Does that help to kind of visualize what's going on a little bit? It's really quick and dirty. If you want me to explain it in more detail later, I can. Now getting into our emergency sources, we have AC electrical emergency sources. The first one I've got shown here is an air-driven generator, and this is made up of 2 parts. So an air-driven generator, common acronym is ADG. The less common acronym is like always directly to ground. If you're on this thing, you want to get on the ground as fast as possible because it means you've lost all engines, typically. So an air-driven generator, it's made up of a ram air turbine and made up of another 3-phase generator, although it's going to have very limited capacity. And when I say a ram air turbine, that is these propeller blades. This thing pops out of the side of the airplane, and at this point, the airplane's probably gliding. You've lost both engines. And as you're gliding, that air passing the fuselage will hit these turbine blades. It's like a big wind turbine, and spin them. So this is a very, very small version of what you see if you go driving, out across Nebraska. Anyone know what I'm talking about? Giant wind farms out there. This is a little tiny wind farm. So it only applies to the most critical equipment. They almost always are automatically controlled. If you lose all electrical power in flight, it automatically pops out. Or they have a manual deploy method as well, a button or a lever or a switch or something. So if we look at it a little closer, here's the generator at the back of it. It's air-cooled now. Got little vents here to air-cool the coils inside of there. And then in the front is our ram air turbine. And now we want to get a specific frequency again. And so it kind of works like a propeller governor in reverse. Inside of this dome is an integral governor. What does an integral governor use? Back to our flyweights again. And what it can do is it can control the pitch of the blades. So if you increase the pitch of the blades, it's going to cause it to spin faster. If you decrease the pitch of the blades, it's going to spin slower. So those flyweights inside the dome, if it's spinning too fast, it gets into an overspeed condition. they're going to move a mechanism that moves the blades to a finer pitch position. And it'll slow down its rotation. And if it gets in an underspeed condition, those flyweights are going to come in. That mechanism is going to cause these blades on the ram air turbine to go to a higher pitch position, and that's going to speed it back up again. And so it's going to maintain a constant speed, even though, as the plane is diving down more or leveling off and its speed is changing, it's going to be able to maintain a fairly consistent RPM and thus a fairly consistent output frequency. Another item we can have is a battery and static inverter. So a static inverter is a solid state device that takes DC and turns it into AC. Okay? So it's powered by the battery hot bus. And remember I said that hot bus earlier is there's nothing between the battery and the hot bus. There's no contactors. Oftentimes there's no current protection. It's wired straight to the battery. And a static inverter will then take that DC. If nothing else is powering the airplane, it'll take DC off the hot bus and provide AC to those critical items that we need for at least 30 minutes at a reduced load. ETOPS requires this to be longer. Extended twin operations over water, you have to have longer sometimes. Okay? But in order to do that, with both a air-driven generator and a battery and inverter setup, we have to load shed. We're not going to be able to run everything on the aircraft. And so the electrical system is able to reduce the loads to match the generation capability that's available. And if it's a battery and inverter system, to match that capability so that it lasts for that 30 minutes or more of that. So extending that source. So the most extreme case is if we have just our essential bus or emergency bus. Oftentimes you have one or the other. It's not all aircraft have both. They'll call it either an essential bus or they'll call it an emergency bus. But if we're down to that, it's going to power some basic flight instruments, and it's going to power just enough hydraulics to maintain control of the aircraft. I'm not 100% sure this is a correct statement, but on the 727, I'm going off memory here, the emergency hydraulics basically gives you half the rudder, because that's got two rudders on it, an upper and a lower. It allows you to move one of the rudder sections, and it allows you to move one or both elevators. I believe it's both elevators. You don't have any aileron control. The ailerons are locked streamlined. So essentially, you can't really roll the plane, but you can kind of side slip it, yaw it, and be able to control pitch. And you're basically gliding it at that point with almost no roll control. Pilots, if you put it into a bit of a side slip, it's going to want to roll a certain amount. You've probably experienced. Anyone done that? I know if you side slip it, the one wing has more air over it than the other, and it causes that wing to drop, and you start to kind of roll a little bit. Am I right? Who's the door? You're am I right? I'm not speaking. Okay, yeah. So by having rudder and elevator, it's enough control to basically be able to do a controlled glide to the ground, and that's all that pump provides. And in terms of instrumentation, basic flight instruments, it essentially gives you one artificial horizon and an airspeed and an altitude indication. And that's all you get to fly it to the ground. And that is the same thing. With air-driven generator like this, the ones I've worked on, this thing is directly wired to the emergency hydraulic pump. If this pops out and starts spinning, you don't have to turn on the emergency pump, it automatically comes on. That's the only, it doesn't power any of the other hydraulic pumps. So this uses load shedding, where all it does is power the essential bus or the emergency bus, and hooked up to that are those minimal equipment you need to get to the ground. And oftentimes it's not even one of your main flight displays. It's like this little tiny, it's like a backup instrument that's about that big. It's got a little tiny artificial horizon in it, a speed tape on one side and an altitude tape on the other, and that's all the instrumentation you get. None of the lights work besides that. that might have a little light in it. Radio, your emergency radio would be the other thing that typically works on there. So you can basically tell your controllers where you're going to be landing. That wraps up electrical. So don't forget